or no? Is it? Or should I convert it? Should I convert this into radians? Is that pi? 180? Or is that professor, is it? Well, 180 times, and the conversion factor to go from degrees to radians, I think it was pi over what, 180? That's the conversion factor. Look at this. These two cancel out. So yes, 180 is equivalent to pi in radians. So if I ask you for the cosine of pi, I'm asking for the x coordinate. Look at this connection here. X coordinate at pi, and the x coordinate was right there. It is staring at me, -1. And that's the cosine. -1 here. Number 3, we'll throw in this. How about the tangent? Let's try 3 pi over 2. Watch what I'm doing here. Not going to be that difficult. 3 pi over 2, guys. 270. I have it in degrees right now. Let's convert 270 real quickly by using that conversion factor pi over 180. Just to see what it looks like in radians. A little awkward, but I could reduce it down by 90. I think 90 goes into 270, what, 3? 90 into 182, so I'm looking at 3 pi over 2. So 270 is equivalent to 3 pi over 2 in this new measure called radians. So when I ask for tan of 3 pi over 2, you'll say, Professor, you're looking at these numbers. And the definition says for tangent, place y over x. That would be placing -1 over 0. You guys agree? Is that what it means to do? Place y over x? Is there an issue there? Yeah, I cannot divide by 0. I can't have a 0 in a denominator. So tan of 270, tan of 3 pi over 2, is undefined. No answer. And sometimes that will happen. Number 4, let's try, I tried sine, cosine, tangent. Let's jump to secant. Let's try secant of, here goes guys, 2 pi. Now someone give me a guess as to where 2 pi is located, and then we'll try to find the coordinates I need. Now guys, 2 pi, where is it?
360.
It's 360, right here. So if you take 360 that I started out with here and convert it, now that conversion factor, pi over 180. I can easily cancel 180 into 360, goes twice. So I'm looking at 2 pi in radians is another way to express 360. Okay, and I'm asking here now, please find secant there, and therefore I'm looking at these coordinates. And secant's definition of there was 1 over x, where the x is 1 for the coordinates, so it's 1 over 1, and there's the secant at 2 pi. Does this make sense, the way we're connecting these? Number 5. I tried secant, let's try cosecant. CSC. Okay, let's see if I can find something else here. Let's go back to pi over 2. Let's go back up here. 90 is equivalent to pi over 2 in radians. So let's try to find cosecant at 90, pi over 2. And if I use the definition, it says place 1 over y, and these are my coordinates. So I'd be placing what? 1 over 1. That's my y coordinate. And therefore we end up with a cosecant at 90, pi over 2 to be a 1. Yes, no. And last one, cotangent. I will just throw at you here cotangent. Let's try cotangent of pi. And again, guys, pi is over here. It's equivalent to 180, 180 degrees, pi in radians. Cotangent's definition says place x over y. I'm looking at these. If I place x over y, I'm placing -1 over 0, which is undefined. Can't do it. Is that true? You just look at the circle and use the definition? Now, if you have the unit circle in front of you, which you will eventually have, of course you can just go through real quickly and just look at the numbers. But you may not have any idea where they came from. At least you have an idea right now where these came from, because I showed you where they came from. Guys, any concerns here? At all? Okay. Now, whew, am I up to, or are you up to me erasing this? And start all over, and this time consider 45. Am I, what even, I watch my time here, I gotta watch the time here. And go through and come up with 45, and go through each quadrant. And label the points for us, like I did for 30. And go from there to there to there. We're supposed to, and when you get this unit circle, it's all there for you. I'd like to show you where some of this came from. I may not do as much with the 45, we'll just get you started here. Okay guys, these definitions though are constant. These definitions are for 30, 45, 10, 5 degrees, 22 degrees, constant here, okay? Let me erase these. I'm gonna jump over here and use these again. Now, this. Let's see what happens. Here goes. This is the last one I'll attempt. Got this put all this together. Let's say we have another angle here. We'll change its size. To 45 degrees, not 30. Let's say it's inside here. Look like that. And let's say this time I'm looking at 45. If that's the way you're going to do, I'm going to close that in a circle. Again, like I did before. Let's try to see if we make it look reasonable. Not bad. And there's 45 enclosed. Now what am I looking for? I'm looking for, as I did for 30, I'm looking for the coordinates of that intersection point. Keep in mind, this is the last one we'll do for you. Show you where these numbers came from. Any suggestions on how to maybe come up with the X and Y coordinates at 45? Anyone? What did I do for 30? Did you guys forget all this in 15 minutes? Mr. Park, you know what, June, Mr. Park, why don't you cut the break time down to 2 minutes? Yeah, 2 minutes rather than 15. You guys are forgetting all this. 15 minutes, we already forgot. What's going on here? Yes. Thank you. Thank you. She's already telling me directly, she's a professor. Go ahead and drop a perpendicular. I'll do it here. And form a right triangle like you did earlier. Just mark it. There you go. Form a right triangle. And she says, Professor, this one may be a little easier than what we did before the break, because I know, and you know, we all know, this up here is another 45 degrees. So I got 45, 45, they call them the isosceles triangle. Now, can anyone tell me anything special that may help me on this one that was not there for the 30-60? May help me on this one to get those coordinates. If I got a 45, 45, two angles are the same size, how about the sides of the triangle? Yeah, two of those sides are the same length. That's what they use when they say the word isosceles. So guys, I'm calling this X. It's unknown right now. This is X. But I do know this is 1. We're still on the unit circle. That radius is 1. That's the radius of the circle, which is now the hypotenuse. And I know those two sides are equivalent. On the side here, if I use Pythagorean theorem, which I can for a right triangle, this one's going to be a little easier. I'm going to get 1 squared, that's hypotenuse squared, which is 1 squared, and the other two sides squared, and they're the same. I got 1 is equal to, collect like terms, 2x squared, divide by 2, no problem. Now, can someone in this clever class tell me, my next step is to take the square root of 1/2. to find the x. Anyone tell me a good way to express square root 1/2? Don't leave that fraction underneath there. Here we go.
Square root 2 divided by 2.
Radical 2 over 2. Right here. And so, Professor, how did that student get that? Well, they more than likely in their mind there, they thought this as split this up. Right, it's radical 1 over radical 2, that's radical 1/2. And you know you can't leave the radical there, you need to rationalize, they call it. So multiply this by radical 2, radical 2. And you end up with radical 2 over, of course, radical 4, which is 2. And that's how we got that. So guys, we'll go back. So this is radical 2 over 2. And this is radical 2 over 2. This one's easier. The two sides are the same. Therefore, I know my coordinates. The x, down on the x-axis, is radical 2 over 2. The y, radical 2 over 2. That's for 45. 30 was radical 3 over 2 and 1/2. This one's much easier. Now, it looks like that. Now, I'm not going to go through all the detail. I went through all 4 quadrants for 30 with you guys. And we just do a couple. Woo! First, let's convert 45 degrees into radian measures, just in case I need it. I know the coordinates of my intersection point. What does 45 degrees look like if I convert it to radian measure? Anyone? Okay, so 45 degrees I'm here, Professor, is the same as if I convert it pi over 4. So I'll keep that in mind. Now, to keep this as brief as I can, because I got other things I got to do here, let's, with your help, let's take this point and reflect it across the y-axis and move it into quadrant 2. This is quadrant 2, quadrant 3, quadrant 4, and you saw me do this for 30 earlier, so let's just take it over. Now, does anyone have an idea, if I'm over there, what would the coordinates be right there for that point?
X is going to be minus.
Here we go.
X is going to be minus.
X will be negative, so it's going to be a negative radical 2 over 2. And the y, I'm assuming, is going to stay the same? That's true, guys? That's this point taken across the y-axis. Woo! Now, if I do this for you, now draw the angle associated with this. If I draw the angle, so Professor, now you're considering this angle. And its size from the initial measure, its size looks like that. Does anyone have an idea what size angle is that? That moves me over into quadrant 2 and has those coordinates. I heard 135. You think it's 135 degrees? I hope it is. 135 degrees. Now, if it is, put it right here. Without me going through a conversion factor, which we could, I could use a conversion formula. Does anyone know what 135 looks like in radians? Well, they like us to express all this in radians. What's 135 look like in radians? 3 pi over 4. You guys could use a conversion factor like you saw me using before the break. 3 pi over 4. Done. And we got negative radical 2 over 2, positive radical 2 over 2. Now, you know I'm not going to do this though. PK, I could do the same thing I did before the break. I could now take it down here in quadrant 3. And ask you what are the coordinates down there. What do you think the coordinates might be without me going through all of it? If I now move down to quadrant 3. In other words, this is reflected through the origin. It's down here. What do you think the coordinates would look like? Just out of curiosity. Negative. In quadrant 3 is going to be negative. Negative what? Radical 2 over 2? And how about the y coordinate? Another negative. They're both negative. So it'll be a negative radical 2 over 2, negative radical 2 over 2 if you're in quadrant 3. Now the harder question is, and I'm going to do it for you, does anyone think they know the size of the angle? If I sketch it from here and go all the way around and go down to this point that PK and I were talking about, that has those coordinates, what size angle is it? Over here, 225. 225. And you could easily convert that to radians. The last one, which I'm not going to do, would be now take this original right here and take it into quadrant 4 down here. Reflect it through the x-axis. Guys, what would the coordinates look like if I took them now down to quadrant 4? What would the coordinates look like there? Radical 2 over 2 stays the same, the x-coordinate, and the y changes into what? Negative radical 2 over 2. So that would be down here, and the last question is, can anyone tell me what size angle would it be, counterclockwise rotation, all the way around, and you stop in quadrant 4? What size is that large angle? I think I heard it. 3 something, what was it? When? I heard you say it. Did I hear you say it? Who was it? Joseph, what was it? 315? 315. 315 degrees. Now, I'm not doing all that business for you. Okay, 45, I did that for you. This was 3 pi over 4, 135. This was 225, 5 pi over 4 if you want to convert. And then the last one given to me was 315, would be the angle. And then radians, that's 7 pi over 4. You'd have all of them in radians. Now, I think I've done enough here. Now let's go on the side here, more important here. Now I'd like to find those 6 trig functions values at, let's do 45. Let's do all 45s here. Okay, sine of 45, that's pi over 4, put it in radians. Well, it says name the y coordinate. Well, the y coordinate's right there. Radical 2 over 2. Cosine, add pi over 4, no problem. Definition on the side there says, please list the x. Well, the x is right there. X coordinate, radical 2 over 2. Tangent, no problem. I don't think it's going to be a problem. Definition says place the y over the x. That would be placing this y coordinate over the x. So you're placing radical 2 over 2 over radical 2 over 2, and we know that's 1. So tan of 45 degrees, tan of pi over 4 is 1. Secant, no problem, I don't think. When we'll find it, definition says place 1 over x. Well, here's the x. So I'm putting 1 over radical 2 over 2. Now guys, I need a clever student, which I have quite a few. Can someone tell me what that looks like? Cleaned up, simplified. I heard just radical 2. Professor, that's just radical 2. If you simplify it. Would you guys agree? If you actually simplify it, rationalize and all that, it's just radical 2 out here. Which makes it nice. Cosecant. This new angle of pi over 4, if I want to find it, definition 1 over y. Well, we're right back into another radical 2 over 2, the y coordinate. And therefore we get the same answer. Rena, you gave me radical 2, right? And then cotangent, the last one, pi over 4, 45 degrees. Definition says place the x over the y. Oh, it's not interesting. Here's the x. Here's the y, they're the same. You're placing radical 2 over 2 over radical 2 over 2. And you're going to get 1. And those are your 6 trig functions values at 45 degrees or pi over 4. Make sense? Okay, now I'm not doing the others for you. I know there's one more special one. I'll get that problem tomorrow for you. I'm not going to derive anything. I'll show you what the numbers are. Oh, geez. Anthony, my concern concern is, you leave me, you go to a calc class, and all of a sudden your professor asks you to find this. And you may look at the professor and say, Professor, did you make a mistake? Did you mean sine of pi over 2? And the professor says, no, I want sine of pi over 12. Then you'll look back and say, Ramsey, don't mention me. Oh, don't you go to a class and mention my name. When we talk, I'll find out. Oh, Ramsey didn't show us pi over 12. Uh-oh. And then the professor would pass in the hallway and say, Ramsey, I had one of your students in class, and I asked him to find sine of pi over 12, and he said you didn't show it. I said, who was it? It was Anthony. Where is he? What time do you have him in class? I'll meet him tomorrow. We'll talk. We'll talk. So Anthony at this point said, Ramsey showed me this. Professor, Math 7 professor, Ramsey showed me that. He didn't show me this. Now, are you going to eventually see this? Yes. You'll eventually see this. By the way, just since I see pi over 12, which is a little strange, let me convert it real quickly and show you in degrees what that angle is. Pi over 12, if I convert it, use my conversion factor. Guys, what is my conversion factor to go back into degrees? Is it 180 over pi? Exactly. That's one of these conversion factors. 180 over pi, pi's canceled. I think 12 goes into this. Help me out. Is that 15? I did quickly. Is that 15?
Yes.
So you're talking about a 15-degree angle. I didn't talk about a 15-degree angle today. Now, what's the most common mistake that you might make? You say, wait, Ramsey, show me something about 30. Could I do half of that? Half of 30 is 15? It doesn't quite work that way. Doesn't quite work that way. Then I heard a student earlier in this class, I forgot who it was, says, if you're looking for 15, Professor, could you eventually maybe, when we move further along and into the trig here, could you actually use what you've sort of shown us today and come up with some way to find 15? Does anyone have an idea where eventually in this class, you'll see a way to find sine of 15 degrees based on what you see right now. And going to what it is, and then we'll get it later. What could you do with what you've seen today to consider 15?
Why divided by this?
Something easier than that. The 15 degrees throws me. It's not a common angle to work with. 45s, 30s, 60s, those are common angles. 15. What could you do maybe with what we have done today, and maybe lead me into something later on, and we'll actually find sine at 15 degrees. Yes? She says take 45, subtract 30. Professor, you did 45 for me. You did 30 before the break. So she says, I'm not going to do all of it today because we can't do it all today. She says, Professor, why not think of, I'm going to do it in degrees here, guys. Think of it like that, and that's 15 degrees. Then that's going to require something else for us to finish up, and I can actually find sine of, Anthony can find sine of pi over 12. Considering 45 subtract 30, but it's going to take a formula to do it. It's not going to take merely a distributive property and all that. It's going to take a formula. You'll see that later on, guys. I thought I'd bring that up. Okay, I'm looking. It looks good. Lord, I was making sense. And June has her job cut out for her tonight. Whoa! With all those beautiful sketches she does for us already, to do this, have you noticed, guys, notice how precise she is? And the sketches, and she's trying to use different colors and show everything. Jeez. And I'm making copies of all this. I'm using it in my next class. Yeah. Guys, any concerns at this point? Nothing at all? Okay, now, woo! Let me see. Are we ready? We're going to definitely get this. This will include something we've done in class today, and I'll try to make some sense of it where these numbers came from. If I just hand this to you and have you memorize like I've seen some instructors do, they'll just hand this and say, here it is. And they use their mind and have no clue where those numbers came from. No clue. Can't do that. You had to do this. Clark, gonna help me out?